Hi ladies and gentlemen, let me wholeheartedly welcome you to the course ECT 204 Signals and Systems. This is the first session on Signals and Systems. This starts with an overview of the course. And myself is Dr. Hari V.S., Associate Professor with the Department of Electronics and Communication, College of Engineering, Chenganur. I also function as a director of the startup company Runwork Research and Solutions Private Limited. So the contents of the today's seminar are your learning outcomes, then we will see the course outcomes, then we will see the 12 national level program outcomes and see how the syllabus tries to achieve the 12 national level outcomes, then why you learn this course, then the approach to the course, and we will discuss a study material. With that we will enter into the course. We will start with an overview of signals, then we will see a broad classification of signals and the summary of understanding. So in this video you will learn the course outcomes, then you will revisit the 12 national level PEOs and understand how the syllabus achieves them. Then you will learn the policies of the course, the approach to the course, and you will appreciate the learning materials. Then you will learn the definition of signal and its broad classification. Then you will appreciate continuous time and discrete time signals. So there are 5 course outcomes. So after the completion of the course, you will be able to one, apply properties of signals and systems to classify them. That is actually the third level of understanding. Then you will learn to represent signals with the help of series and transforms, such as Fourier series, Fourier transforms, etc. Then the third outcome is you will describe the orthogonality of signals and you will understand the convolution integral. Then the fourth outcome is you will apply a transfer function to compute the LTI response to input signals. Then the fifth outcome is you will apply sampling theorem to discretize continuous time signals. Well, there are 12 national level program outcomes. First and foremost is the engineering knowledge, that is to how to apply the knowledge in mathematics, science and engineering fundamentals to solve a complex engineering problem. So that most of the syllabus material, most of the subjects do meet this criterion. Then the problem analysis, identify, formulate, then review literature, then analyze complex problems to solve that. So the problem analysis, of course this is a problem oriented paper, this is quite of a problem solving type paper. Then you will see the design and development of solutions, that is how to create solutions, how to develop solutions for complex problems. This paper, Signals and Systems, address a lot of design issues. Then conduct investigations of complex problems, use research based knowledge and research methods including design of experiments, analysis and interpretation of data in many complex problems. Then the fifth one is the modern tool usage. Here in this course we will be using a lot of simulations, mostly with Python and its tools. Then the laboratory you may use the hardware like the dedicated DSP hardware for doing this. So the modern tool usage is also addressed in this course. Then the engineer and society, of course it goes without saying that whatever we do, that is for enhancing the value of someone in society. Then the environment and sustainability. Then the ethics, that goes without saying. Whatever work we are taking up, the ethical values should be, ethical responsibilities should be taken care of. And individual and teamwork, how to function as a team for building projects and all that. That is also our syllabus addresses that issue also. Then the communication, effective communication between the team and all that. Then the project management and finance. Then lifelong learning, that goes without saying. That is in the during your professional life, the subjects imparts a lot of ideas for your professional life. And the five COs we so earlier, they should have relations with these POs. So the CO-PO relation, if you look into that, the COs of the syllabus of the subject should have a strong correlation with the majority of 12 PEOs. Now, when it comes to why you should learn this, why you should listen to this series of lectures, is that this course gives you the foundation for the future course, digital signal processing. Then both the signals and system course and the digital signal processing course will train you to build a DSP hardware which are central to communication systems. Again, most mobile technologies rely on DSP process. So programming DSP is a skill much wanted in the wireless communication industry. Then this subject also lays a foundation for image processing, computer vision, etc. The skill to manipulate AI, discrete data is very useful in modern subjects like data analysis, AI applications, etc. Now, as far as approach to the course is concerned, there will be some 45 to 48 theory sessions with the simulations in Python. So I will be using Python 3 to perform these simulations. Then all you students are directed to install Python 3. I strongly advise that you have a Linux system. The most user-friendly Linux system may be Ubuntu. You can install Ubuntu 22.0 for LTS, the long-time support, and in your laptop, and install Python 3 along with that. So as usual, my series tests will be based on, they will all be open examinations. So they will be based on problem sets, and the problem sets will be published some 2 weeks before your tests. So many other, if possible, many other tutorials will also be given. And the assignments will be computational ones with Python 3. So overall, the course will be a problem and practical oriented type. And when it comes to the study material, so you can learn signals and systems. First you have to understand the theory, then you have to solve as many problems from this, then you have to perform a lot of simulations. So first when it comes to the theory part, I strongly advise that you read the book Signals and Systems by Alan V. Oppenheim and Wilsky. And you can also read the book Signals and System by Simon Haken. And you can do the problems from the Shom outline series. One is a theory and problems in signals and systems by Su, and Shom outline series on digital signal processing by Munson Hayes. Both are available in our library. All these books are available in the library. You can refer them. And when it comes to simulations, you have to do a lot of Python simulation. You must have a flavor of Python programming in your scientific computing laboratory, and if you need further ideas on Python programming, you can read the book a primer on scientific programming with Python. Then you can do the exercise from that book, or if you start from the very basic things of Python, it is wise you read the book, read and do the codes in the book, automate the boring stuff with Python. Now we actually entered into the subject. We will see an overview of signals. So electrical signals are of immense importance in communication engineering, biomedical engineering, electrical control, instrumentation systems, space engineering. A lot of applications are there. And sometimes we encounter non-electrical signals also, like in non-electrical signals find application in data analysis, machine learning, image processing, etc. And when we look at what a signal is a function on independent variables. Okay, a function is a mapping from a domain to a codomain. Okay, so there are some independent variables, and a signal is a function in independent variables. So these variables can be temporal or spatial, or can be both. Okay, most electrical signals you observe in your lab on CRO, etc., are temporal signals that are observed at a given spatial point. Say you measure the voltage across some resistor. These are temporal signals that you observe at some spatial point. But there are temporal signals also. For example, if you take your ECG signal, it has both the spatial and temporal variations, because it has spatial variation because it is these signals are taken from 12 positions on the human body, and it has a temporal variation too. And if you look at natural images from camera, they are digital camera or scanner, they are spatial signals. ECG signals are both spatial and temporal, and if you look at the seismic signals are both spatial and temporal. And variations in stock prices, fluctuation in interest rates, etc., they are non-electrical random signals. So signals can be non-electrical too. And we will start with a very broad classification of signals. That is, signals are broadly classified into a continuous time, or popularly known as the analog signal, or a discrete time signal, or a discrete signal. So in many cases, the independent variable can be time. Okay. And if this independent variable, in most cases it is time, if it is a continuous function, then the signal is a continuous time signal. For example, if you look at a speech signal from a microphone or seismic signal from a seismic sensor, they are all continuous time signals. But sometimes if the independent variable is discrete, it's a discrete time signal. For example, if you run a temperature, or if you run a fever, and if you are hospitalized in the hospital, say every hour the nurse comes and takes your temperature and records in a chart. It's a discrete measurement, like if you have a 39 degree at some point, say at 7 o'clock, say 39.5 degree at say 8 o'clock. Okay. So that's a discrete kind of measurement. So if you come here, if you look at a continuous time signal, the left signal, this signal is this signal is a continuous time signal. This signal from a microphone captured and plotted with Python. And this is a discrete time signal, because these values occur at discrete intervals of time. If you look here, this time axis is continuous. Here the time axis is not continuous, it's a discrete value. So if you look at that here, this is a continuous time signal. So here you can see that if you take a very small interval of time, say delta t, you can see that this function has infinite value. This x of t has infinite values in the small interval delta t. However small this delta t is, you can have infinitely many values for xt. And this time axis is continuous. But if you look here, if you look at this signal, here you can have this is a temperature measurement of a patient. Okay, so here you can see that it's some 37.4 degree at say 0 t, and at 1 t, say this is say 7 a.m. and this is say 8 a.m. this is say 9 a.m. Here it is a 38.8 degree, this is a 39.0 degree. Okay, so this way. So if you ask me what is the temperature between 7 o'clock and 8 o'clock, I cannot say that, because the function is not defined there. Okay, so here you can see that the time axis is discrete. So the function is defined for nt only, say like 0 t, the function has a value say 0 t, say 7 a.m. or say 1 t, say 8 a.m. Or say 2 t. What's the value between 1 t and 2 t? We cannot say that, because the function is not defined there. And also the discrete signal xt has only finite number of values. For any time interval, if I take it, has only a finite number of values. So discrete interval, the discrete signal is undefined between nt and n plus 1t. So if what is the patient's temperature between 7 a.m. and 8 a.m., because there is no such recording. The function does not exist there. Don't say the function is 0. The function is not 0. The function does not exist there. And when you come to the summary of understanding, here in this session you learned the course outcomes, then you revisited the 12 national level program outcomes, and you understood how the syllabus strives to achieve them. Then you understood the policies of the course and the approach to the course, and you appreciated the learning materials. We discussed the learning material for the theory, the problems, and the simulations. Then you learned the definition of signal and its broad classification. Then you appreciated the continuous time and discrete signals. And that is the end of today's presentation. Thank you all.